All right, so let's see this particular question now. So in this question, we are given a sorted and a rotated array, right? And when we say a sorted array, we mean sorted in increasing order, right? So we are given a sorted and a rotated array of distinct elements, right? And our task is to find the index of a target key, right? So we are given another input integer key, and we need to find the index of this particular key integer, right, in this particular input array, right? So for example, if you see this input array 5 6 7 8 9 10 1 2 3, right, and the key over here is 3, so we need to return the index of this 3 in this particular input array, right, which is 8 over here. So our output will be 8, right? So that's what we need to do in this particular problem. Now maybe you can just pause this video over here and try to think of a solution, and once you are done, you can just come back and check the solution. Okay, so now to solve this particular question, see, one way is to apply linear search, of course, and we can just keep traversing this particular array, and wherever we get, the current element equal to key, we can just return that same index as our output, right? But that will be linear search, and the time complexity will be order of n, right? But now, since we are given for a fact that the given array is sorted, right, we can actually think of applying binary search over here. Now, of course, it is rotated also, but then it is sorted, right? And so we can actually think of a way of actually applying binary search over here, right? So now one observation over here is that, this entire array, since it is sorted and rotated, we can happily conclude, we can very comfortably conclude that it will be actually divided into two arrays, right, which will be sorted in themselves, right? So for example, if you see over here, this is the point of rotation, which means all the elements from this particular element till the end, right, and all the elements before this particular element are sorted in themselves, right? If you see from 5 to 10, all the elements will be sorted, and all the elements from 1 to 3 are sorted in themselves, right? So now if I'm able to find this point of rotation, right, that will actually help me in dividing this entire array into two different sorted arrays, right? And then what I can do is I can just apply binary search in these two individual arrays separately, right? And find out the index wherever it is present, right? And to find this particular element, the point of rotation, this is something that we have already done in the last question, and I would highly encourage you to solve that particular question first if you haven't done so far. It is pretty much the same thing that we have to do over here. But like, just to give you a little recap, what we can do is, we can keep dividing this original array into two halves, right, using binary search, and we can keep moving always towards the unsorted part, right? For example, if I divide this particular array into two halves, I think this will be my mid, right? 9 will be my mid, and then I will move towards the right half of this particular array because that is unsorted, right? Left half is already sorted, right? And why I will always move towards the unsorted part of the unsorted half of the array, because that unsorted half will be where my point of rotation will be, right? Because at my point of rotation, there will be a violation of the sorting order, right? And since there will be a violation of the sorted order that will make that entire part of the array unsorted, right? That's why I have to keep dividing the entire array into two halves in every binary search, and then I will always keep moving towards the unsorted part, right? And I will just discard the sorted part, and then once I'm left with just one element, that will be my point of rotation, right? And that element I can use to actually divide my entire array into two sorted arrays, right? So that's how I'm going to solve this particular question, and that point of rotation will also be my minimum element of the entire array, right? That's what we have seen in the last question, but then that is a little irrelevant over here. We are not going to make use of that fact much over here, but then just to let you know, that is going to be the minimum element as well. Wherever we are actually starting the rotation, that is always going to be the minimum element, right? That's how the rotation works, right? So all what we need to do is we need to find this particular element, the point of rotation, and then we can apply binary search on these two individual sorted arrays, right? And see, I don't even need to like apply binary search twice, like on both the arrays individually, both the sorted arrays individually. What I can do is I can just have a little condition over here that if my key is lesser than or equal to the last element of the array, it would mean that the key is actually present in this right half, right? because see, it is lesser than or equal to. If it is equal to the last element, then I've already got the index. But then if it is lesser than, the last element, that means it is somewhere over here, right? But if it is greater than the last element, that means it is in this part, right? In the larger part, in the rotated part, right? And that's why then I will apply binary search over here instead of applying it on the right half, right? So that way I can just like compare the key with the last element of the array. If it is greater than the last element, then definitely it is not present over here. And if at all it is present in this entire array, it will be only present in this particular half, the left half, right? And if it is lesser than the last element, then it will be present in the right half, right? So that's what we need to do over here. I hope you understood the intuition well. And if you talk about the time complexity over here, again, we are not like, we are just, applying binary search over here, and we are just applying it 2 times. First to like get the point of rotation, and then to actually figure out the index of this particular key in either of the two sorted halves that we got, right? So that's why the time complexity over here will be order of log n, right? And the space complexity will be constant since we are not using any extra space over here, so it will be order of 1, right? So that's the entire solution to this particular problem. Now let's jump to our ID and implement this particular solution. All right, so now let's implement the solution that we discussed. So now let me just declare a function over here. I can just name it as search, right? And this will accept an input array, integer array, and an integer variable called key, right? And what I can do is I can first of all capture the length of this input array in a variable n, right? And then I can declare my left and the right pointer for the binary search, right? Like this. So this is something that I can do. And now what I need to do is I first of all need to find the point of rotation, right, of this entire array, right? And for doing that, I can now apply binary search. I can have, a while loop while L is less than R, right? And then I can just calculate my mid in every iteration, right? It will be L plus R divided by 2, right? And now what I need to do is I need to move towards the unsorted half of the array, right? And now to figure out which one is the unsorted half, whether it is the right half or the left half where the array is unsorted actually, what I can do is I can compare the element at the mid position, the current mid position, with the element at the right position, right? That is the last element of the current array, right? I can compare those two, and if my current element at the mid position is actually greater than my current element at the right position, it would mean that the right half is actually unsorted, right? Because see, ideally, if this right half was actually sorted, the element at the mid position would have been lesser than the right element at the right position, right? Because my array is sorted in the increasing order, right? But since I'm getting otherwise, it would mean that the right half is actually unsorted. And since it is unsorted, I can conclude that my point of rotation will actually be present in the right half, right? So now I need to move to the right half. And for moving to the right half, I will just increment my left pointer to mid plus 1, right? I will move towards the right half, right? That's what I will do. And in case, if that's not the case, if my right half is actually sorted, it would mean my left half is unsorted. And so now I will do R equal to mid, right? And why I would do R equal to mid and not mid minus 1? Because see, we are saying that all the elements right from mid, starting from the mid till the last element are sorted, right? Because see, we got array of mid lesser than array of R. That means all the elements starting from mid till the R are sorted, right? That means even mid could actually qualify to be that point of rotation, right? It could very well be the first element in the second sorted array, right? So I hope you got the idea why we are doing R equal to mid and not R equal to mid minus 1 over here, right? So now we will just continue with this while loop. And now once we get L equal to R, it would mean that, we are just left with one single element now, and we will come out of this while loop, right? And that single element will actually be our point of rotation, right? So that's why now what we can do is, like what we can conclude is that all the elements from, L till n minus 1, that is the last element, are constitute one sorted array, and all the elements before the L pointer constitute another sorted array, right? That's how this particular element at L is actually dividing the entire array, the original array, into two individual sorted arrays, right? That's what we can conclude, right? I hope you understood this, and this is the same thing that we have done in the last question, in the previous question. So this should be clear by now, right? So now what I have to do is, now I have to figure out whether this given key is actually present in the in the right sorted array or in the left sorted array, right? And to figure that out, what I can do is I can compare if my key is actually lesser than or equal to the last element of the array, right? So if it is lesser than or equal to the last element of the array, it would mean that it is contained in the right half, in the right sorted array, right? In the second sorted array of the two sorted arrays that we have got, it is present in the right sorted array, right? And so what I can do is I can just apply binary search, right, on the right sorted array. So I haven't declared this binary search function yet. I can just declare it in a second, but this is how I will do it. I will just pass the input array, the key that I have to find, the the L index, that will be the starting index, and the end index, that will be n minus 1, right? That's what I will do. And see, if that is not the case, then it would mean that the key, this particular element, is actually present in the left sorted array, right? In the first sorted array actually, right? And to do that, like, now I can apply a binary search on the left array then, right? I can actually copy this entire thing over here, paste it over here, and now see, my starting index will be 0, right? I will be starting from the first index, and I will be going till L minus 1, right? That's how my entire array has been divided into two, like, different sorted arrays, right? So one is starting from 0 to L minus 1, and the other one is starting from L till the last element. So essentially what we are doing is we are just checking if my key is actually present in the right part of the array. Then I'm just applying binary search on this particular array, right, on the right array. And if it is not present in the right array, if it is like the key is actually greater than the last element, the greatest element of the right sorted array, then it should be present in the left sorted array, right? And so I can just apply binary search on the left array then, right? So that is fine. But then what if my L over here is actually equal to 0, right? That is, my point of rotation is equal to 0. It would mean that I only have one array which is actually the original input array, and there is no rotation in this particular array, and so I cannot divide this particular array into two sorted arrays individually, right? Because there is no rotation at all, right? And so I will have to actually check that condition before actually applying binary search on the left sorted array, right? So what I can do is I can just put a small condition over here that if my L is actually greater than 0, only then I need to apply binary search on the left sorted array. If it is lesser than 0, or if it is equal to 0, then I can actually say that this particular element is not present at all in the entire input array, and I can just return -1, right? So that's what I need to do. This is the entire implementation. And also, like, I can just implement this particular function. I can do that quickly. Maybe it is going to be the standard binary search function that we have, but I can just quickly write it over here, right? It will accept array key values of L and R, right? The start and the end index for the binary search, right? And then I can just run a while loop while L is less than equal to R, right? And I can calculate mid in every iteration like this, and I can keep checking if my array of mid is equal to key, then I can just return the mid index, right? Else if my array of mid is actually greater than key, like this, then I can just apply binary search on the left half of the array, right? And if it is lesser than key, right, that is in the else condition, I can just apply binary search in the right half of the array, like this, right? And if this particular element is not at all present in the input array, then I can just return -1, right? So that is going to be my binary search function, which I'm going to utilize over here, right? So I hope you understood this particular solution, this entire implementation well. And we have already discussed about the time complexity. It is going to be order of log n, and space complexity will be order of 1, right? So now I will see you in the next video. Thank you.